Hello, this is a tutorial on how to find derivatives or how to analyze graphs of derivatives and justify your answers both orally and in written form. We will not be looking at function notation and finding increasing and decreasing intervals. We're going to analyze graphs today. So we're going to go through some examples on how to analyze some graphs. So, first off, we have this function, x squared minus 3x minus 1 over x minus 2. Now, we're going to find the local extremum and determine the intervals of which the function is increasing and decreasing. And we're going to use this by using derivatives, and we're going to justify our answer of the values that we found. So, the first off, to find this, we have this function, and what we're going to do is we're going to analyze it by finding the increasing and decreasing intervals. Now, we can put this in our calculator, and we will. But we're going to first look at this by taking the derivative. Okay, so we're going to find the derivative because the first step is we want to find our critical points. All right, our critical numbers. All right, and that's when f prime equals 0 and when f prime of x does not exist, or where it's undefined. So the first thing is we're going to find the zeros, or derivative of f of x. So we're going to use the quotient rule, and what we have is 2x minus 3 times the bottom, which is x minus 2. Minus the derivative of the bottom, which is 1, times the top, which is x squared minus 3x minus 4, all over the bottom squared or the denominator squared, and we have that. Now, we're going to take this and set it equal to 0 to find our critical points. All right, first part, we have our critical points. All right, when this equals 0, we're going to take our numerator now, set equals 0, because that's when the function, this rational function will equal 0. So we're going to first simplify it, so we have 2x squared, we have minus 3x, we have minus 4x, we have negative x squared plus 3x plus 4, and we're going to set that equal to 0. So this is the numerator equal to 0, and now we're going to simplify. We have x squared, these cancel out, x squared, we're left with negative 4x, and we have plus 4 right here, and now we're going to find these zeros. So we factor it, and we realize we have minus 2, x minus 2. So we have a critical number at x equaling 2. We also want to look at our denominator right here. And actually maybe a different color. I'm going to say the denominator is in green. So the numerator we look for the zeros is in red. And so now we're going to take the denominator, which is x minus 2 squared. We want to set that equal to 0 because we want to find out where this is undefined, okay, where that does not exist, right there. All right, so when we do that, we realize that, once again, this is at x equaling 2. All right, x equaling 2. Well, that's kind of interesting, because what we realize is that our numerator and our denominator happen to be the same values. Now, that's, we'll pause, all right, but we'll check this out, because now we do our sign chart. So we have our 2 right here. That seems to be a very interesting function that we have. All right, so we go 2 to infinity, and we're going to test it out. So we're going to plug this into our derivative. Looking at our total derivative, which is on top right here, we're going to test out our values, and we can simplify it right here. And it appears that this is going to equal, well, if we plug in 0, we should get a positive value, and then when we plug in 3, we should get another positive value. So it appears that f is going to be, f is going to be increasing and increasing. Increasing and increasing. Now, with that, okay, all right, we take that and we realize that if we have this correct, it's going to be increasing and decreasing. Now, I am a little bit intrigued by this, maybe you are too, that we have 2, and that happened to be the same critical point for both. So that should tell us something, all right? If you look at the original function, it appears that the original function, we write this out, is at 2. We have this right here, which is going to give us, if we factor this, x minus 4, and then it's going to be x plus 1 over x minus 2. All right, well, it appears that we have right here a vertical asymptote right here at x equaling 2. So I'm going to check this one out. Let's see if we did it right. All right, whenever I have this is where the calculator comes in handy. So if you take out your calculator, all right, I'm going to pause this and get it get my calculator going. So you take this right here, all right, and we're going to, long one, pause this. So take it out and graph this function that we have right here, all right? So take your calculators out and graph that function. Welcome back. All right, so I put in the calculator. Make sure you put the numerator, all right, and the denominator right here, all right, both as in parentheses. So I put in my calculator, and when you see this, when you graph it, you get this graph. I'll bring this out here, and let's look at this. Now, according to this graph, it appears that we have a vertical asymptote here at 2. That's why it's going up like that. And we were aware of that. That's what we learned in Chapter 2, all right, with rational functions. And now what we see is that this is increasing to the left of 2, and it also is increasing to the right of 2. Well, that's pretty awesome, because if you recall, when we did our analysis, we found the same thing. When we write this, what we have found is that because of the vertical asymptote, right, there will not be a maximum, plus there's no sign change. But what we found is that f, and this is how we're going to justify our answer, f is increasing on the intervals from negative infinity to 2 and 2 to infinity, because what do we find? Because f prime, its derivative, is positive on both of those intervals. All right, that is positive. There is no maximum for this function because there is no sign change of the derivative. Also, 2, this critical number, is also a vertical asymptote, so there wouldn't be a value when we plug in the original function. And also, there's no decreasing intervals because it's never negative. So what we did was, through our analysis, we verified what this graph would look like. Pretty impressive. And when we justify our answer, we are writing out what we found. We begin with our subject, f, all right, is increasing, so our function is increasing, all right, using a little notation, on the intervals from what are intervals out, where it is increasing, because f prime is positive, and that's the reason why we thought that. All right, well, let's try another one. All right, so that was pretty cool. Let's try this one. Now, this one is one of our basic graphs, or our basic functions. Okay, so this one will also, we're going to do some graph analysis and then justify our answer, what we found. We're going to try to find some local extremum and determine the intervals in which it is increasing or decreasing. So let's find this out. All right, so to try this, we're going to first find our critical numbers. First step, same thing. Y prime, find out where it's 0, and we'll also find where it does not exist. Okay. So we find this one, y prime should equal negative 1/2 x plus 2 to the negative 1/2 power times the inside represent chain rule, which is 1, so I'll just put 1 there. We'll simplify this function, and we have negative 1 over 2 times the square root of x plus 2. Okay, so that is our derivative. Now looking at this, is this ever equal to 0? No, the numerator will never equal 0. All right, so it'll never equal 0. All right, will it ever not exist? Well, if you look at the bottom, all right, obviously it can't be negative, so look at the bottom, where does it not exist? And it appears not to exist when the denominator equals 0, okay, and that would be when x equals negative 2. All right, so we find a critical number at negative 2. So we go over here, and we are going to do our sign chart, okay, and we're going to take this, we're going to plug the value in, negative 2, we have negative infinity to negative 2, and we have negative 2 to infinity. And when we plug this in for our y prime, we plug in 0, and we realize that when we plug in 0, we get a negative value. And when we plug in, oops, not 0, I apologize. When we plug in 0 right here, we get a negative value. It looks like that. All right, and over here, okay, what we have is when we plug in negative 3, let's go negative 3, let's go 0 because that's on the interval. Look at negative 3, we get actually an imaginary number because we get 2 over the square root of negative 1. Well, that is an imaginary, all right, and we are not looking for imaginary values. We are looking for real answers, so this is not in our domain, and that was not in the domain of our original function because, if you recall, this is one of those basic square root functions. All right, so we, once again, for this one, it appears, according to our analysis, we found that y is decreasing on the interval -2 to infinity, because, hopefully you know why, we're looking at this right here, because y prime is negative on that interval. That is why it will be decreasing. And we could write in here y decreasing if we wish. We have that. Now, that shouldn't come to no surprise to us, because this is a very familiar basic graph. We have the square root function, which originally looks like so. We call it the little teapot function. That one is being shifted over to the left 2, and then is being reflected, right, over the x-axis, all right, and then is shifted down 4. So we're going to go 1, 2, 3, 4, and so you have a graph that looks like this, which is constantly decreasing from -2 to infinity. So that makes sense. Well, that's pretty cool, all right? And we found all this out. We could look at our graph, or we could have, all right, did our analysis, but we did our analysis because that helps us define what we're looking for. All right, final one, okay? We have another one. We're going to justify this one, okay? This is a piecewise graph, so this is a little bit more complex. Okay, a little more complex. All right. We're going to try to justify our answers with this one. We're going to be decreasing and decreasing. Okay. Now with this complex function, it's piecewise, what we have is, well, we're going to find its derivative. We're going to find its critical points. Okay, its critical values. Well, we're going to find out right here. We see there's going to be a switch. All right, so there might be discontinuity there. So plug that in there. We kind of look at this. Plug in 0. On this side, when x equals 0, we get 3. When x equals 0 on this one, we get 1. So there is discontinuity. All right, so there's going to be discontinuity at 0. So actually, where does y prime not exist? Right off the bat, we know because this graph right here, which is a parabola for all the values which are less than 0, and another parabola for all the values greater than and equal to 0, because that is discontinuity at x equals 0, that is actually one of our critical points. X equaling 0 is one of our critical points. Okay, so we're going to test that out. We are now going to find y prime. Now to find y prime, we're going to actually find the derivative of the top and bottom. So we have -2x for all x values less than 0. And we're going to find out right here, okay, we're going to actually have 2x for all x values which are greater than 0. We're not going to include 0, all right, because actually there is no derivative at 0 because there is discontinuity right here. All right, that's why we don't include equaling to 0. All right, and that pretty much sums it up, because from right here, where does this function equal 0? Well, it would be 0 at 0, but that's where it is discontinuity. So this is our only critical value. Okay? So, if you look at this, when will this equal 0? When does y prime equal 0? At 0. All right, well, we already said it was 0, so where does this equal 0? Y prime equals 0. Also at 0, well, it's already discontinuous there. There is no 0 there. All right, so that's what we got. Okay, so just kind of try to explain that a little bit better. I don't know if I did. Hopefully you understand. All right, so we're going to do an analysis. We're going to start at 0, and we're going to go from -infinity to 0, and then 0 to infinity, like so. And what we have is y prime. We're going to test this out both sides, so I'm going to plug in values less than 0, so like -1, I plug it in there. All right, values less than 1, I get positive value. All right, so that means that y is going to be increasing on this value because y prime is positive. I plug in a 1 in here, it's also going to be positive, so it appears that this one is also increasing, all right, on this interval. Okay, so what do we just find? Well, justifying our answer, once again. Y is increasing on the intervals -infinity to 0 and 0 to infinity, because y prime is positive. All right, so we checked that one out. Now to make it a little bit nicer, let's check out the graph as well. I'm actually going to put in this calculator. We're actually going to sketch out this graph. We're going to graph this section first for the piecewise, for all values less than or equal to 0. I'm going to plug in 0 in here, and I get 3. 1, 2, 3. It's going to be an open circle right there. Values less, I'm going to plug in, I don't know, well, anything. It's going to be a parabola. That's actually going to be shifted up 3, then reflected. So I'm just going to go right like this. All right. Just a sketch. All right. The 0, I guess the 0 would be at the square root of 3. Right there. All right. Okay. And on the other side, our negative square root of 3. Okay. And over here, what we have is another one. So in this one right here, once again, now I'm going to start at 0 again. If we realize this one is going to be actually an open or closed circle because it is equal, right, at 0. And this one is going to go up like this parabola. All right, so we have these two parabolas. All right, we cut in half. We can see that there is a change. Now, because of discontinuity, their derivative doesn't exist because it has to be, all right, continuous in order to have a derivative. But we can also see that, yes, in fact, this graph increases at 0 and then continues to increase as you go to infinity on the other side of 0. So once again, our analysis, all right, using the derivative and using our sign chart, okay, identified, all right, what is happening to this graph. Okay, so with that, you can finish up this assignment. We can also now finish up one other assignment that I gave you. All right, and this one right here, I would ask you for this one. These 1, 2, 3, 4, 5 problems. If you would please write out and justify your answers. All right, for those problems right there. Write out and justify your answers of where the functions, after you do your analysis, where do the functions increase and decrease. Write that out because that's when y prime is positive, when y prime is negative. All right, and also if you have any max or mins, all right, with those. All right, so that was a tutorial. If you have any other questions, you can ask. Okay, and yeah, so enjoy.